So hi, I'm Graham. I'm a mechanical engineering graduate, I guess. I have my bachelor's in mechanical engineering. I'm currently studying to get my motorsport engineering master's, which is very niche, but it's kind of the thing I'm interested in. But I am just curious about trying to improve my skill set, and I guess one of the ways I figured I could do that is sort of by throwing together these videos and compiling this stuff so that I have, something to try to basically produce that I can prove to myself, like, okay, I've done this, I know how to do this sort of thing. I'm going to try to keep this short and sweet. But yeah, I just want to have some sort of repository or, whatever you want to call it, like a collection of stuff I can refer back to, just even if I just want to be able to refer back to it as material to teach myself, because it'll give me the highlights, or I don't know, just something I can use to remind, maybe teach others if others find this stuff, but also just remind myself of what I've done in the past. So yeah, I guess this is primarily focused on like certain topics. The thing that kind of sparked this interest was some numerical methods. And I wanted to start there and basically just see if I can't teach myself some of these things. Yeah. So let's see how this goes. So I'm gonna try to keep things kind of short and sweet. Keep this as like sort of a good summary of the concept. So essentially, the first thing I want to talk about is our numerical methods. Specifically the bisection method. This is, the simplest thing that you can do in order to solve for the zeros in any given curve of, that you could give to a computer. And so essentially numerical methods, as a quick summary, are methods that are used by computers to determine certain, answers that we could otherwise derive for ourselves mathematically in the real world, using more complex methods, right? If I, as a human, were looking at a equation that I was trying to find these zeros for of some curve, I could essentially just, do something like factoring and essentially pull all the roots from that equation if it were something like a polynomial or what have you. And by doing that, I'd very easily be able to determine what all the roots were, even if they're decimals or whatever it is. I'd be able to determine it via just sort of like a simple method like factoring. The computer, unless we can program it to think like us, it can't effectively do that, at least with the simply less complex methods that we have now. I don't know what modern AI is capable of, but anyways, the point is with these more complex or these rather complex things that we want these computers to be able to do, but you want to be able to make them do it very simply in very simple terms. We have these things called numerical methods, and that's essentially what I just want to talk about, which is, so the first option for finding zeros of a curve would be using the bisection method. It's a very rudimentary, very simple, basically gonna fail if you don't give it a lot of precautions and fixes. But essentially the bisection method is the simplest way to start out by giving the computer a few different pieces of information about the curve and then telling it to go from there. Okay, so the bisection method is a method for which we're essentially describing only a continuous function, so the intermediate value theorem must apply. And essentially what we're looking at is a curve for which we know that there is a certain bounding of x values upon which that we know there is some zero. So we can say from the value x equals a to x equals b, inclusive that there is some zero along these points. So what the bisection method essentially, the naming of it essentially refers to literally cutting these values in half and saying, okay, let's just create a value in between them. So what we'll do is we'll create a c, and that c will be equal to the average of the two values. and that will be our point in the middle, exactly halfway between them. And what we'll then say is, okay, well, we know that for any continuous function, which means that, if you're drawing this with a pencil on a piece of paper, you're never lifting the pencil up. So for a continuous function on this range, we know that if the value of the function ever goes from negative to then positive, or vice versa, positive to then negative, we know that in both of these cases, there must be then some zero on that range. So the thing that we're looking for is essentially this flip. If I see this flip happen anywhere, we know that there must be some zero on that range. So what we're going to start out by doing is we're going to evaluate our function at C and say, okay, we want to find out what the value of f of C is. And the exact value is less important, but what's more important is the sign of it. So we'll start out with, okay, so it's either positive or it's negative. And so in any case, we want to know its sign. And then what we say is, okay, if we then evaluate f of a and determine that f of a happens to be the opposite, sorry, my handwriting is a little bit sloppy, opposite of f of c, then what we can then say is there must be some zero on that range for a to c, right? And so what that essentially is indicating to us is that there's a zero on that range. Same thing goes for B. So we'll continue to do that. So if f of B opposite, then if f of B is opposite f of C, then we know that the zero must be on that range. And so of course you can see how the logic gets a little fuzzy here. So it is totally possible that if you have a large enough range of values that you have some sort of function where both of these cases actually ends up being true. So it's totally possible that you get a value from A to C flipping, as well as the value from or the sign from C to B switching as well. So that's where the bisection method becomes a little bit difficult to use when you're evaluating functions that have multiple zeros over the range that you're evaluating. So that's where it becomes a little bit tricky, but in this case, we're sort of assuming simplest cases, continuous function, and essentially there's only one zero on the range for which we're defining this function. Okay, so then when it comes to actually putting this theory into effect, what we're going to be looking for is essentially, our function, some sort of arbitrary function that we can actually evaluate at every point, and it's continuous. And so what we're going to look for is a certain range. So we're given, say we plug into our computer calculator. We're going to say, okay, let's evaluate along the range of, if we say this is, for whatever reason, we'll say x equals -1 and x equals say 5 up here. So we're gonna evaluate on the range -1 and 5, right? So then what we got to do is come up with our new value c, and that's going to be the middle point of both of these values. So if we add these up and divide by 2, we're going to get 3 from this one, so this will end up being 2. And so let's just say that 2 happens to land right about here. So this is x equals 2. And so now what we have is essentially this, effect going on where we see that we have two positive value or two negative values here on this side and a positive value over here. But let's go through that more thoroughly. So based on what we had written earlier, we had said, okay, so let's evaluate f of c. So f of c here, we can clearly see is a negative value. So we're going to point out this is negative. If we evaluate f of a we can see is clearly a negative value because it's below this line. Sorry, rather just negative. And then of course f of b we see is up here, and this happens to be a very positive value. And so, of course, if we go through our little path of logic that we had earlier, what we look at is we see, okay, f of a and f of c happen to be both negative, both the same sign. They're not opposites. Therefore, 0 is not on that range. But then if we look over at f of b, we see that f of c going over to f of b, there's actually a flip from negative to positive. That flip indicates some negative. So what we're going to do is we're going to reset our bounds, and we're going to treat now 2 and 5 as our new boundary. So we're going to, instead of using -1 like we did before, we're going to say, okay, 2 is now our left bound, 5 is now our right bound, and then we start the process over again. So we can do the same thing again, where we say, okay, average of 2 and 5 is going to be about 3.5. Well, I guess I'll just kind of arbitrarily put this here, but plugging that in, plugging that value in, we can see here that this is a positive value. We do the same thing at f of, I guess we can call it f of a now, but 2, f of a, it's still a very negative value. And then f of b again, still a very positive value, right? So let's go through the logic again. If we say, okay, f of a and going to f of c, we see, okay, flips from negative to positive. We see, okay, that means that there's likely a 0 on this range. And just going back and checking again, f of c going to f of b, we see that both values are positive, and therefore there is no 0 on that range. So then the process starts over again. So then we go again down to 2, and 3.5 is now our range over which we're acting. And you see this is basically just a repetitive process. And in theory, unless for whatever reason you happen to get a boundary that lands exactly on your 0, but essentially in theory, this could go on forever. And this is part of the thing with numerical methods, is that they're not perfect, right? They're not going to produce a perfect 0, at least a good amount of the time. But what they're going to do is they're going to create a very, very close value to that final value, and that's going to be dependent on the tolerance that you give it. So the tolerance, or essentially the error, is the value that you're happy with being off by, right? So you're going to end up getting down to a point where these bounds are, say this point is like 2.2, right? And you end up getting bounds around this 2.2 value being like maybe your bounds are like 2.21 and your lower bound is like 2.195, right? Like you're very, very, very close, and essentially either one of these values are going to give you the 0 which you're looking for, but you just have to determine, okay, at what point is it not useful for me to continue cutting down and going closer and closer? At what point am I just happy with getting some value and then using that for whatever other function you're going to plug this into, right? So eventually you're going to say, okay, I want a tolerance of a value less than 1e to the -4 or whatever, or 1e of -4, and that's the tolerance I want between these two values here. But any lower than that, it's not really worth my time, so I'm not going to bother processing that deep. So that's essentially where you get finished with this numerical method of the bisection method. And I guess what we can do now is sort of implement that into some Python code and show you how that works in a sort of actual application rather than in MS Paint. So I think now comes the time to actually put this into effect. I'm going to do this in Python using the Spider IDE. I like it because it operates similar to MATLAB, which I'm very used to. But of course, this works, with any coding language. I'm just doing this because I'm not a coder and I know how to use very basic scripting. But point still stands that you can put this into any sort of code and make it run and get relatively quick solution. So what I'm going to do with, I'm just basically start by importing NumPy. I don't really need this. I just do this for one line. I'm not sure why I do this, but and then the next thing we're going to do is we're going to set up our function for the bisection method. So the bisection method, we're just going to call it, we're going to define it as bisection itself, and then we're going to have these inputs A and B like we described, and that's going to be our range of x values along which we believe there is a 0. And so then what we're going to give it is we're going to give it some tolerance that we decide. I'll say 1e to the negative 3. And it's essentially just, the difference between A and B that we're going to be happy with in the end once we actually evaluate go to running the program. And then we're going to say, okay, once it gets to this difference between A and B, we're happy with that. We're going to determine the real difference between A and B as being equal to the absolute value of A minus B. And we're just going to have that as a value that we use to basically check in to make sure that our function actually continues to run until that until those values are less than that tolerance. So we're going to say while the real difference is greater than or equal to the tolerance, we're then going to execute this, series of processes that we basically just kind of talked about in the prior part of this video. So we're going to say that, take our C value, we're going to say that, okay, C is equal to the halfway point between A and B, or it's the average of the two, same thing. And then we're going to say this value can be evaluated at, we're going to evaluate this C value, call it f of C or FC. And then what we're going to do is we're going to call this some, I'm just going to call it polyfunc because that's what I'm going to call it later on, but it's just executing or evaluating this, actually evaluating this value using a function that I'll determine later on. So that'll be f of C. We're going to do the same thing, f of A, polyfunc for A, and then the same thing, fb equals polyfunc for B. So then what we're going to say is this condition. So, and I guess another way that you can very simply check if things are the same sign or not the same sign would be if the things multiplied by each other are producing a positive or a negative, right? So essentially, if two things are positive, what happens? And you multiply them. The product of two positives will be a positive. The product of two negatives will be a positive. And the product of a negative and a positive will be a negative, right? So that's kind of what we're looking for. Is essentially we're saying, okay, we know that if the signs are the same, they will always produce a positive value in the end. And if the two signs are opposites, they will produce a negative value. So what we were talking about earlier, we were just kind of saying it verbally, like if these things are opposite of each other. But in this case, what we're doing is we're simply just doing the mathematical execution of this and just saying if we multiply these things, we know that they're the same signs if the resulting product is positive, and we know that they're opposite signs if the resulting product is negative. So what we're going to do is we're going to then say, okay, I'm going to put this in as a precautionary measure just to make sure that we don't actually start to try and evaluate functions that have more than one zero. So I'm going to check that, okay, f of A times f of C is less than 0, and if f of B times f of C is also less than 0, then we have an issue on our hands, because that means that both of these things we're in multiple cases checking, in multiple cases we're seeing that there are multiple zeros, right? So that would be essentially return for this function. We say more than one root on range. So that's an issue, and basically we're just saying we can't solve that, at least right now, with this method. And then the next situation that could be an option is if f of A times f of C is less than 0. So if just f of A and f of A and f of C are less than 0, which means they're both they're opposite signs of each other, then we're going to say that B is now equal to C, right? So we're setting up what we kind of discussed earlier, which is you're resetting that C value to now be part of that range of the sort of boundary where we're executing across. So we're going to reset the B value in this function that we call B to be the same value as the C. And then in the same situation, but on the other side, we're going to say, f of B times f of C is, if that's less than 0, then the opposite is going to be the case. We're going to say A is now equal to the value of C. and then else, right? So else, this is if basically none of these cases trigger, and if we basically say every value we evaluated is positive or every value we evaluated was negative, then we're going to say, okay, there are, return no roots on range. And so that's essentially what we're saying is nothing got triggered in all these cases. So we're just dealing with essentially something that is either essentially that is something that has no zeros, or this is also a very possible case, we are getting essentially something that has a lot more zeros than we were expecting, and now we're triggering a bunch of positive values, but there actually happens to be a lot more zeros going on. So in either case of these end conditions, we're not going to be able to evaluate it, at least with the way that we're setting this up currently. And then what we're going to do is we're going to say simply the root range that we now are using is this numpy times, or is this numpy array that we're setting up. I'm doing this, I don't know why, I'm just deciding to do it this way. And then we're going to return this root range, and you'll notice that this is outside the while loop. So after the while loop has finished executing, and now the real difference is less than this tolerance. So once the real difference is less than the tolerance that we've allowed, then we're going to break this while loop and then come out of this and say, okay, set up this these sets of values. This is our new boundary around which we are confident the value's in there somewhere. And then we're going to return that array. And then what we also have to do is define our actual function. So we're going to define the polyfunc that I wrote earlier, and we're going to call that just x. And then we're going to say the f value is equal to x cubed. In this case, we're going to use a really simple one that we know for a fact has 1, 0 along its whole range. And then we're going to use return f val. And so really simply, if we call this and just decide arbitrarily, okay, let's just say -5 to 10, then we're going to say, okay, we're going to execute this function. And what should happen is that we're going to get sort of an array that shows us the range around which we believe this value is in, and we've decided that we have a tolerance of 1e to the -3, and so we should see a 1e to the -3 difference between those two values. So if we run this, we'll see that we get no roots on range. That is fantastic. I have no clue why that happened. Okay, so, and right, naturally, of course, I missed something. And of course, the thing I missed was that I forgot to reestablish what the actual difference is between our two values. So this should fix our issue. So, of course, after you run the whole thing, after the while loop almost completes, you should be then at the end determining, okay, what is the actual difference now between our new A and B values, to then reevaluate that against the tolerance. And so, of course, once you do this, say we wanted to just evaluate across, -1 and 8, then we're going to hit that, and that should give us a value very close to the actual answer. So if I'm not so if we can check this against something like Desmos. Desmos will tell us for the function x cubed minus 1.5 that we have 1 and only 0 at 1.145. So what we're doing here is getting a range of values that is, very, very, very close to being just around that value. So 1.145, a little bit above that and a little bit below that. That's not so bad. And so what you can do is, choose one of these values to be your answer, or if you wanted to be, very prudent and you wanted to just round it to something near, then you could do that. But yeah, so effectively, this is sort of the coded up version of the bisection method, and there's lots more precautions you can put in place, probably lots of methods you can use to cut this better up if you have more than 1 0, but this is what the simplest implementation of this looks like.